So we talked last time about parametric equations and how they work. We didn't really do any calculus with those types of equations though, so now we'll see how we deal with the calculus of equations like this. So remember what they do. You have a graph, each parametric equation, set of parametric equations, there's one for x and one for y, produces a graph with that, depending on what that variable t, what it does. And so since it has a graph associated with it, we can then talk about the slopes of tangent lines for that graph. So that's what we'll talk about today. All right, so you can see on the top of the 10.2 worksheet there, the idea here is that, if we remember, we've got x is some differentiable function of time and y is some other function of time, both of them being functions of this other variable t. So if you want to take the derivative, say dy dt, we have to actually use the chain rule for that. As you can see there, we have to differentiate the function y with respect to the variable x, because as we've seen, we can take that function of y, this function here, y as a function of t, and we can make it a function of x if we replace the t, if we solve for t and then plug in that x function, right? So in other words, we can make y into a function of x. Y can be written as some other function of x there, okay? So the chain rule then tells us that if we want to take the derivative of y with respect to this variable t, we need to first differentiate with respect to x, and then the chain rule says we then multiply that by the derivative of x with respect to time. So this gets multiplied by dx dt. So this is the chain rule, and then really what we're after here is how do we figure out what dy dx is, because as we've seen, when we draw these parametrically defined functions, we draw them on the xy plane. And so when we're asking about the derivative, we want it to be dy dx, because that's what we'll be seeing on the graph. Okay, so if we solve this for dy dx, you can see we can divide, we get dy dt over dx dt. And so this is a formula that we need to remember. This is how you differentiate with respect, differentiate a parametrically defined function on the xy plane, okay? So as we remember, again, both x and y are functions of time, so you can see what you have to do to differentiate this thing to get that derivative. You have to first differentiate the function of y with respect to time, then the one with x, divide the two of them. That gives you the slope of the tangent line on the xy coordinate plane, okay? And then the second derivative, really what you can, I think the best way to view that second derivative is like this. When another way to write that first derivative is like this. You can say in that numerator, this is the same as d by dt of y over, I'll just leave the denominator the same, dx dt. Okay, so really what we're doing when we want to find the first derivative is we're going to plug that y function in right there, okay? That means the exact same thing as this, okay? And so if you want to take the second derivative, then that is to take the derivative of the derivative. Again, right here is we're taking the derivative of the function. If I want to take the derivative of the derivative, then what I would do is this. This is, remember, the Leibniz notation for the second derivative. Instead of putting y here, right, that's what I had there before is y. So still going to say dx dt. What am I going to put there? Well, not the function, but the first derivative. So that's what you have to do to take that second derivative, is just replace that y in the numerator with the derivative dy dx. Okay, and we'll see kind of what that means here in a second here if I want to find that second derivative. All right, so let's try this for example 1. All right, I'm going to write this second one as 1 plus t to the 1/2 power. Okay, and the goal here again is to find dy dx. In other words, what would the slope of the tangent line be, of any tangent line be, if we were to graph this parametrically defined function on the Cartesian coordinates system? Okay, so according to the formula, what do we need to know? We need to know dx dt, right, dx dt, and that one we can use the quotient rule to do that. So low d high, so 1 plus t. D high is just going to be 1 minus high d low, right? So the top function times the derivative of the bottom, in that case it's also just 1 there. And then over the bottom function squared. So you can see what happens there. The t's cancel and you're just left with 1 over 1 plus t squared. Okay, and then the derivative dy dt, the other one that we need, just 1/2 1 plus t to the minus 1/2. And the chain rule here is just going to be a 1 there, so it's just 1 over 2 times the square root of 1 plus t. Okay, so putting those together, dy dx then must be dy dt, so that's this 1 over 2 square root 1 plus t over dx dt 1 over 1 plus t squared. You can simplify that, make that 1 over, I'm going to go ahead and rewrite that as a fractional exponent again. The denominator, you can invert it and multiply, so 1 plus t squared over 1. Right? Multiply these, we're left with 1 plus t squared over 2 times 1 plus t to the 1/2. And then this, if you notice, we can actually simplify that a little bit with properties of exponents, right? These are the same things here. This and this are the same. So you can subtract those exponents and make that 1/2 1 plus t to the 3/2 power. All right, so no questions there. If not, we'll go on to the second example. All right, so here, this one is actually asking for the equation of the tangent line, and then we want to graph the curve and the tangent line together. And we want to find the equation of the tangent line at that point, 0, 2. All right, so we'll first find the two things that we need, dx dt and dy dt. So this is the first one requires a chain rule, so we'll have pi cosine pi t for that derivative, and then dy dt is be 2t plus 1. So according to our formula, the derivative here, dy dx, is equal to dy dt, 2t plus 1 over pi cosine pi t. Okay, so we want to find this quantity at that point, 0, 2. So we'll just plug in, no, actually, before we do that, let me point something out on this. So they want us to find the slope of the derivative basically at this point, 0, 2 here. But what we aren't really, well, what we have to notice on this particular derivative is that it is given in terms of t, right? There's no x's and y's here, but this is an x value and this is a y value. So what we need to do is think about what t value is going to produce that particular point. And usually on these problems, it's going to be fairly straightforward what is going to make that happen. You can actually even solve for it, right? Like if the x value is 0, which it says here, you could plug in 0 here for x and then solve for t. And then the y value is 2, so you could plug in 2 here and solve for t. However, that's not 100% necessary, because in this particular case, you might be able to just guess what that t value is that's going to produce that particular point. Notice when t equals, let's see, if I put 0 in there, that's probably not going to work, but try t equals 1. If t equals 1, then you're going to get x equals the sine of pi, right? And what's the sine of pi? Isn't that 0? And then y is going to be equal to 1 squared plus 1, which is indeed 2, right? And so that actually does produce the point that we're looking for. So the t value that produces that point is t equals 1, okay? Does that make sense what I'm saying there? And then, like I said, if that wasn't entirely obvious, which on most of these questions it actually is pretty obvious, like t is probably just going to be 0, 1, maybe 2, something like that. if it's not obvious, like I said, you can always just set the x to 0 there. You could set the y to 2 there, and then solve for t that way. And then the t value that corresponds to both of them, that would be the one that you're interested in. Anyway, so what we want here is we want dy dt when at that point 0, 2, but we now know that that actually occurs when t is equal to 1. So we'll go ahead and just plug that in. So 2 times 1 plus 1 over pi cosine pi times 1, that's just cosine pi. So we're going to get 2 plus 1 is 3 over, and then the cosine of pi is negative 1, right? So we're going to get negative pi over here. So we're going to get, for the slope, negative 3 over pi. Okay, now that is the slope of the tangent line, right? And so what we need, though, is the equation of the tangent line. So we know now that we'll have a line that has this equation, negative 3 over pi, y equals negative 3 over pi x plus b. And then we can find out what that b is because we know that this thing passes through that point 0, 2, right? And so when x is 0, y must be 2. That's the point that it goes through, right? And so basically we'll plug in 2 here, 0 here. But this works the same way as it does in a normal Cartesian equation in that since we're graphing on the xy plane, if you know what the y-intercept is, then that in fact is the value of b. And we're seeing the same thing happening here, right? B is equal to 2. So the equation of our tangent line then must be y equals negative 3 over pi plus 2, x plus 2. So we want to graph this function that we started with, x equals sine pi t. So I'm going to change this, x equals sine pi t, y equals, change the y1, that's going to be t squared plus t. Let's check out the tangent line graph, right? And so we said the tangent line was y equals negative 3 over pi x plus 2. Okay, so if you look at that graph, is it pretty obvious what's going on there? There's the point of intersection, right? 0, 2. That definitely looks like a tangent line for this graph. So I think that's a good indication that we did everything correctly there. So that verifies that we have done the right thing there, I think. Let's go ahead and move on to the next one. Okay, so let's take a look at that third example. So this is the one that where we'll get to practice taking that second derivative. Okay, so there's our function. Find the, and then there's a question about concavity on there, so we'll have to remember our how we approach that with regular Cartesian defined functions. Thinking back to calculus 1 there, basically. Okay, so anytime you need to find the second derivative of a function, of course, you have to also find the first derivative, so let's do that. So to find the first derivative here, we need to know what dx dt is, we need to know what dy dt is, and then plug it into that formula for dy dx. So dy dx is dy dt, that's e to the t over dx dt, 2t, okay? All right, then to find the second derivative, we use this formula. That is the first derivative d by dt with respect to time of dy dx divided by dx dt. That's the formula we have to use. Okay, so you can see kind of what's happening here. What this is indicating that we have to do is take the derivative with respect to t of that quantity right there. Okay, but we have that quantity right there. There it is. Okay, so we could even write this with that actual function. We could say this is equal to d by dt of that thing we just got, e to the t over 2t, divided by dx dt. And in fact, let's go ahead and put the dx dt there as well. Dx dt is just 2t. Okay, so everybody's seeing what's going on here, how this process works. And so that thing in the numerator is telling us, well, we now have to differentiate that first derivative with respect to time. Okay, that's then going to require the quotient rule, right? Because that's a quotient, e to the t over 2t. So low d high minus high d low, and then the bottom function derivative is just 2, all divided by the bottom function squared, so 2t quantity squared, and then this is also getting divided by the 2t, okay? So what I have here, that is this, that's the derivative of that first derivative that we just got with respect to t, and then the 2t down here is just hanging out. Okay, everybody clear with that? Any questions? And if you wanted to, you could write that like over 1 to see that we have a complex fraction here. So let's simplify that numerator and go ahead and flip that denominator fraction over. So we'll get in the numerator here 2t e to the t minus 2e to the t divided by 4t squared. Multiply that thing by this bottom one flipped over, so 1 over 2t, and then combine all this stuff, we get 2t e to the t. In fact, let's go ahead and factor out that e to the t. So we'll get e to the t, and we can even factor a 2 out of there as well. Let's do that. Factor out a 2 e to the t. That'll leave us with t minus 1. This denominator, 8t cubed. Okay, now they're also asking us to identify the which values of t this thing is concave up. Okay, so if you remember from your Calculus 1 class how you have to deal with this, remember for finding intervals of concavity, what you have to do is find any place where that second derivative is either 0 or undefined. Okay, so where is this second derivative equal to 0? So to do that, we can set the numerator of this equal to 0, set that equal to 0. That gives us two things set equal to 0. And then this one has no solution. There's no way that's going to equal 0. So that means that t equals 1 is a potential inflection point, a potential place where concavity could change. And then also notice that we have another potential inflection point where the second derivative doesn't exist. That comes from this denominator term here, right? If the second derivative doesn't exist, that is also a place where a function could potentially change from being concave up to concave down. And so from that one, we get another potential inflection point, setting the denominator function equal to 0, 8t to the third equals 0. Well, that clearly has one solution, t equal to 0. So both t equals 0 and t equals 1 are potential points of inflection. And so remember the process for this whole thing is you find every place where the second derivative is either 0 or doesn't exist. You set up an interval for values depending on what you got for those solutions. And so our interval is going to look like negative infinity up to 0. And we're just going to make sure we could put those in there. Yeah, these are not restricted from the domain or anything. And then we go from 0 up to the first place, or the other place where the second derivative is 0 or undefined, and then up to infinity. Okay, and then remember what you have to do with this. You make a table of values. You guys remember this from Calculus 1? This is kind of like, first you did it with the first derivative to determine where the function was either increasing or decreasing. Then you do it with the second derivative, the same thing, to find where the function is concave up or down, and also to locate inflection points. And so on the table, this is kind of what you would want to do with the table. And so we pick test values. That's what the TV stands for, test values. So we pick any number on this interval from negative infinity to 0. We'll pick negative 1 on that interval. We'll pick 1/2 on this interval. And we'll pick 2 on that interval. Okay, so now we'll come back up and just look at that second derivative. Again, we're looking right here, this thing. And we want to determine the sign of the second derivative. Okay, so if I plug in negative 1 there, you can see what determines the sign of this thing, right? There's this quantity right here, and then there's this t in the denominator. Those are the two things that are going to determine the sign of the second derivative. If I plug in -1, look what happens to the numerator. -1, the numerator will be negative. If I plug -1 into the denominator and cube it, it will also be negative. So I have two negatives, and so the result is a positive value. Okay, if I plug in 1/2, look what happens. If I plug in 1/2 there, the numerator is negative. The denominator is positive though, right? And so that makes a negative number. So in this part, the second derivative is negative. If I plug in 2 to this thing, notice the entire thing is positive, and so there we go. So our conclusion is that the function is concave up, and then it's concave down, and then it's concave up again. Okay, and this idea of concavity is exactly the same as concavity for a regular defined function, in that on the actual graph of the function, if it's concave up, you should see like an upward shaping bowl situation. If it's concave down, it should be like a downward shaping bowl. Okay, so let's take a look at the graph and see and just verify that it really kind of does look like that. So I'm going to share the Desmos again, and we'll take a look at the graph. Okay, so in this case, I want to change the x value to, let's just get rid of that line as well, we don't need that. Let's change the x value to t squared plus 1. Change the y value to e to the t minus 1. Okay, and in fact, actually, for the little bit where the function is concave down, it's kind of hard to see this here, but let's do one thing here. The interval is 0 to 1, where it's actually concave down, okay? So if I change that from 0 to 1, this bit here is the bit that's concave down. And you can kind of see it does look slightly like a downward shaping bowl right there. In fact, that's the only part of the graph that is concave down. The rest of it, this part up here, again, it's kind of hard to see that that really is a place where the second derivative doesn't exist, but it's going to turn around there and become concave up after that. And then from the part below it, I think that's clearly concave up if you look at what it was doing after that. And so if you look, for example, do that minus 10 to 10 again. Yeah, this part is clearly concave up. You can kind of see that upward bowl shape right there. Harder to see that that part is actually concave down, but it really is. And then you kind of see that it does actually bend back upward there. So it is concave up. A little hard to see there, but it is. The math is telling us that it is, so it is. All right, let's go ahead and talk about how to find areas under parametrically defined curves. All right, so to find areas under parametrically defined curves. So kind of what we're doing here is we just saw how to deal with like the calculus 1 aspect of this, right, really quickly. How do you find tangent lines, right? So now we're going to look at the calculus 2 stuff, or most of calculus 2. That's what we've been seeing. Integration, right? Definite integral. So this is the idea. For parametrically defined curves, we remember that x is defined to be some function of time, y is defined to be some other function of time. You can write this dx dt, and kind of just combine our Leibniz notation with the function notation, is equal to f prime of t, and then you can get the differential for this. Dx is equal to f prime of t dt, and you can do similar for here. Dy is equal to g prime of t dt. Okay, and so when we find areas under curves, typically what we do in just the normal function notation is, suppose I want to find the area under this curve f of x, whatever that happens to be. Well, the way that we have this defined as far as parametrically defined curves, we could call that y dx, right? Because f of x and y are kind of used interchangeably, right? And so, well, what is y though? Y is that function here, the g of t function, okay? So you could say that this is, and actually when we change it to t, the t parameter, we change the the bounds as well. For whatever reason, they use alpha and beta here, I think, for the book, but I'll just stick with what they do. The y value we call it g of t, and notice that this does actually make sense that this is going to have to change because this thing has a dx on it, right? And when you remember that when we change the variable to something else by some kind of a substitution, the bounds will also change. Okay, so that's why that's happening. And then just look up here and see what dx is. Dx is f prime of t dt. Okay, so that's the formula to find the area under a parametrically defined curve between two t values in this case. Okay, let's see how that works in an example. So check example 4 to just see what we're looking at here, and then we'll look at a graph too, and you can kind of get a sense of what's happening. It says find the area enclosed by this curve x equals y equals root t and the y-axis. Okay, so if you want to see kind of what region this is, let's go ahead and just graph it so you can take a look at it, and then we'll come back and go through the math about how we actually get this answer here. Okay, so let's go back to Desmos here, and I'm going to change this to be the new function we're looking at here, x equals t squared minus 2t. Okay, so you see what the graph kind of looks like here. What we're really interested in, it says also bounded by the x-axis, right? Sorry, the y-axis. So if you look at the shape of the graph, the only pieces that are going to be bounded would be right there. And you can kind of see that what are we really looking for? Like if we didn't see this graph here, what would we be, how would we determine what these bounds are? You could see if I started at 0, for example, starting it at 0 basically means that it's going to start at the origin, and then it sort of does that winding thing, and then it hits the y-axis for some t value. Well, what we're interested in is what that t value is, because once we figure that out, then that will be the top bound, right? You see what I'm saying? There will be a t value that corresponds to that part hitting the y-axis there. So what we're trying to do is find that, okay? Now, if you think about algebraically speaking, how do we do that? Well, what's true about x when we hit that point right there, right on the y-axis? Well, if you're on the y-axis, isn't x equal to 0? And so in order to figure out that t value where we enclose that little bit of the graph, we just need to set the x value equal to 0, and that will tell us, okay? And algebraically speaking, what I want to do is figure out, again, what is the t value when x is equal to 0, okay? So if I set the x equal to 0, and then I can factor a t out of that. And so I get t equals 0 and t equals 2. Okay, so then if we were to go back to the graph and stop the t value at 2, you would see that would be the place where it hits the y-axis. That region right there that we saw to the left of the y-axis, that's what we're actually trying to find the area of. Okay, so we've determined our t bounds. So now all that's left to do is just plug stuff in. This formula here, remember I changed the y into the y was the g function here, right? And then the dx, that included this stuff here. And so what we want to put first is the y function in the radical there, okay? And so the integral we want to find, the area, is going to be integral from 0 to 2. Put the y function first, so I'm going to write it as t to the 1/2. And then we need the dx as well. So let's find that. Dx is going to be equal to 2t minus 2 dt, and so that's what goes here. 2t minus 2 dt. And then we can find that integral by distributing. Why are we only setting the x one equal to 0? Okay, so that's specific to this problem. It may not be that way. But let me go ahead and just show the graph again, and maybe that'll answer the question. according to the description of this problem, they want us to find the area enclosed by that function, the parametrically defined function, and the y-axis, right? That's what it says in the problem, yeah. And so if you look at the graph of the function, what we're interested in then, and let me change this bound to 2. What we're interested in is this piece of the graph, really what piece is like right here, right inside this, right? And so since it says it's bounded by the y-axis, right, that's important. And you look at the function, the function and the y-axis. What we're looking for then, well, if it's bounded by the y-axis, we need to know the t-values for which it actually touches the y-axis, because the only way it's going to be bounded by the y-axis is if it touches the y-axis in 2 different places, right? Otherwise, it can't be bounded by anything in the y-axis, right? And so in order to figure out where it actually touches the y-axis, well, we got to think, well, what's true about x when you're touching the y-axis, right? Well, what's true about x when you're touching the y-axis? X is 0, right? And so that's why we had to set just the x equal to 0 to do that, okay? To find those t-values. Now, suppose the question was worded differently and we had a different function, right? Like suppose we had a function that was touched the x-axis in 2 places, right? Suppose that happened. The function maybe come up, hit the x-axis somewhere, rose up, and then hit it again later, right? And it said, find the area bounded by the function and the x-axis. If the question was worded that way, then what would we have to do? Well, touching the x-axis means what's true about y. Y is 0, and so we would set the y values equal to 0 and find the t values that correspond to y being equal to 0 in that case. Does that make sense, kind of why we're doing the x one here in this case? Again, that's just because of this particular problem. Could be different in a different problem. So I hope that answered your question. All right, so to finish this off, we just need to find our okay, cool, good, I'm glad that helped. We need to find our antiderivative here, and so we'll have a 5 halves power, so we need to multiply that by 2/5. We're going to get 4/5 t to the 5 halves power. Raise that to the 3 halves power, we're going to need 2/3 in front, so we'll get 4/3 there, t to the 3 halves. And we've got to plug in 0 and 2 to that thing. So plugging in 0 is not going to do anything. Plugging in 2, we'll get 4/5 times 2 to the 5 halves power minus 4/3 times 2 to the 3 halves power. So there's not much else we can do to simplify this, and there's probably a couple things, but it doesn't matter too much. That's the exact solution right there. That whatever that number happens to be, that's going to be the area enclosed by that piece of the curve from where t is equal to 0 to t equals 2. All right, so we've kind of zipped through both branches of calculus for parametric equations, doing some of the things that we talked about. And if you remember, one of the other things that we talked about with the definite integral was finding arc lengths for curves. Well, parametrically defined curves also have arc lengths associated with them. And so the next thing you see there is finding the arc length of a parametrically defined curve. The way this works, let me just kind of derive the formula for you real quick here, how that works. So if you remember the formula for regular arc lengths, it was this. This is just regular old y equals f of x type function. So what if we want to do this parametrically instead? Well, what we can do is rewrite what dy dx actually is. So I'm just going to change this a little bit and say, well, what is dy dx actually in parametric form? Well, remember, it's this. It's dy dt over dx dt, right? We just saw that. And so all I'm doing here is just replacing the dy dx with what it is in parametric form, okay? And so let's go through a little bit of a simplification here and see what happens to this thing. Now I'm going to go ahead and factor out that 1 over dx dt term there. And so if I do that, I'll be left with a dx dt squared here. And you can just, if you want to verify that all this is correct, you can just distribute that back in there. And then notice that 1 over dx dt term under the radical. Since it's squared, it can be brought out of the radical. If you take it out of the radical, just also remember that it's in the denominator, right? If you factor out that, if you take the square root and take that thing out of the radical, it's 1 over dx dt, right? But then that can actually be flipped over and written as dt dx. Okay, see that? So I'm doing two steps at once there. I'm taking the square root of it. That puts me at 1 over dx dt, but 1 over dx dt is the same as dt dx. And then notice that on the end there, I've got that dx, but look, those dx's can cancel, and we're just left with a dt there. So at that point, since we're now changed to a new integral in terms of t, this is where I change the bounds as well. And so the new integral here, one that we want, is the one that you see on the paper there with a dt on the end of it. Okay, so that's the derivation of the formula that we are seeing on the page there. Okay, then let's just see an example of this. All right, so to do this arc length here, we need to know what is dx dt. So dx dt in this case is 6t, dy dt is 6t squared. Okay, so according to our formula, the arc length must be the integral from 0 to 1 of the square root of dx dt squared, so that's going to be 36t squared, and then plus dy dt squared, that's going to be 36t to the fourth. And then to evaluate this thing, we can notice that in that radical, we can actually factor out a 36t squared. And if you do that, that's going to leave you 1 plus t squared, right? 1 plus t squared. Okay, and then that 36t squared, that's a perfect square, and so you can take that out of the radical. That'll leave us with a 6t outside. I'll go ahead and take the 6 and just put it outside of the integral altogether, and then the t can stay, and then we're left with the square root of 1 plus t squared. And so you can see how they kind of think about making these problems so that they're doable for us. This one is a nice, easy substitution integral. So we could say that u is equal to 1 plus t squared, du is equal to 2t dt. So here we can notice that we actually have a 6t dt, right? And we've got a 2t dt in our derivative there. So if I want to just turn that into a 6 right away, I can just multiply both sides by 3. So 3 du is equal to 6t dt. So in our new integral, the one that has u's instead of t's, we can write it as 3 integral, and that's going to end up being root u du. And then we also have to change the bounds, right? The lower bound was 0. Now it's going to be 1, right? And then the old upper bound was 1, and now it's going to be 2, it looks like. Now remember, that is u to the 1/2 power, so we could raise that by 1. We get 3/2, so we'll put a 2/3 u to the 3/2, evaluated from 1 to 2. Those 3's are going to cancel nicely, so we'll just get a 2 there. So our final answer will be 2 times 2 to the 3/2 minus 2 times 1 to the 3/2, which is just 2. Okay, so there it is. That then is the length of that, the arc of that parametrically defined curve, if we let it trace out part of the curve that goes from t equals 0 to t equals 1. Okay, and then the next one is surface area, and that's very similar to the way that we describe surface area with normal, regular Cartesian functions. So the surface area, they call it S. Notice the 2 pi is still there. Just remember what the formula was for regular defined functions. How did we do it? Well, there was a y here, right? And so it's exactly the same, really. With parametric, you still just put the y there. And in these cases, we're only going to be concerned about revolving this around the x-axis. We're not going to bother with revolving around the y-axis here, so this is the only formula we need here. Although you certainly could revolve these around the y-axis as well, but that's not something we're going to bother with in this course. Okay, so there it is. That's the formula for surface area. All right, well, there's 4 problems there. Go ahead and try to work on these. I'll give you maybe 10, 15 minutes to do that. All right, let's take a look at some of these problems here. All right, so that first one is just asking us to find the derivative, and I think actually that's the same. I just screw up on my part. That's the same function that I did in the example, so we can skip that one. Well, thanks for doing it again anyway, Michael. And then for the second one is the second derivative, and let's see. Yeah, so in order to do that, again, the idea, first find the first derivative, so that's what he's doing here. First derivative of both the y1 and the x1. Simplify these derivatives, and that's what you find. Yeah, so there's the first derivative, and then he's doing this separately. The formula for the second derivative does require us to find this quantity here, right? That's what goes in the numerator of the second derivative. So that's what he's doing there. Just taking the derivative of this thing, get that quantity right there. Then the second derivative is, yeah, so you're just multiplying by dt dx. That's the same thing as dividing by dx dt, in case you guys are wondering that. Take the answer that you got from the d by dt of dy dx, that's this one right there, put that there, divide it by dx dt, but that's the same as multiplying by the reciprocal of dx dt, which is this, right? Dx dt is here, so we're just flipping it over, and then multiply it through, and you get that there. And then to determine, let's see, this one asking for, yeah, concavity again. So remember that these technically aren't called critical numbers, since we're not dealing with the first derivative here. So I guess critical values is probably a good thing to say. But basically, that's anywhere where the second derivative is not defined or is 0. Okay, so basically to find those places where the second derivative is either 0 or not defined, you set both the numerator and the denominator of that second derivative equal to 0. So if you set the numerator equal to 0, that's where you get this one, right? That's the 0 critical value. And then if you set the denominator to 0, you get the other critical value of 1. Okay, so both of these places are really what we would call them as potential points of inflection, places where the concavity could change. Okay, and so how do you determine whether the concavity is going to change or not? This is where I set up the table, right? And so we pick critical values to do that. So Michael's doing that on a number line here. So picking a number that is less than 0, that's what he's doing here, -1, plugging it into that second derivative, finding that we get a negative number there, right? So since we're getting a negative number, the down arrow indicates concave down. So it's concave down in this area, in this region. And then plugging in another critical, or a test value really, 1/2, that's what he's doing here, plugging in 1/2 since it's on this region, right, from 0 to 1. Plugging in 1/2 gives, what is this? A positive number, right? And so that's telling us that this function is concave up in that region from 0 to 1. Finally, plugging in a number here in this region here, 2 is a perfectly fine test value, so he's plugging in 2. Plug all that in, you get a negative number, and so what happens now? It goes back to being concave down again. Okay? So that's, again, it's the calculus 1 procedure, but it's using this new type of function that we didn't see in calculus 1, right? The parametrically defined equations. Then number 3, area enclosed by a parametrically defined function. So again, how do you do that? It's the integral of y dx, right? But dx is equal to the f prime of t dt. And so here's the y, right? This is the y. And then all of this is the, or I guess we call it, what do we call it? F prime of x, f prime of t, sorry, dt. Right, so this is the g of t, f prime of t dt. Okay, and then just multiply that out. That gets you your integral there. And then that's a pretty simple integral. Just plow through it, get 24/5. And finally, the surface area. Now, I remember this being a pretty difficult problem just because it's kind of tedious what you have to go through. It looks like it is kind of a tedious problem. Yeah, so dx dt is this, dy dt is this, and then you square them and add them together, you get this mess here, all of this, right? And then notice what Michael's doing with that other part of it, the y that you have to put there. He's just incorporating it into the radical there, you see? Because this is a root, right? There's a root there, and then there's another root, so you can take that t and just put it under the radical with the rest of it. Okay, yeah, now at this point here, this is where it's kind of hard to see, but that thing factors to be that thing right there. Perfect square trinomial. In fact, what I would, it's pretty hard for most people, I think, to spot that. So I'm just off to the side here, going to just show another, maybe more detailed way to get from that one step to the other step there. So we're at this point here, right? 16t cubed plus 8. And I would call it, I mean, some people can certainly see that that is going to factor. Personally, I would have a hard time seeing that that's going to factor to be 4t to the 3 halves power plus t to the minus 3 halves power. That's pretty hard for most people to spot. So I would actually take it from here and say, okay, what if I wanted to find an LCD here, right? The LCD in this case is that, t to the third, right? And so what I would do is say, well, I'm going to multiply this by t to the third over t to the third, because it needs to have that t to the third in the denominator. I would also multiply this by t to the third over t to the third. And what is that going to give when you do that? You're going to get 16t to the sixth plus 8t to the third plus 1, and all this will then be over that LCD of t to the third. And that might be a little bit easier to see that that numerator is indeed the difference of, or sorry, a perfect square trinomial, and it factors to be 4t to the third plus 1 quantity squared. Okay, so I don't know if that helps that much or not, but there you go. That's another way to look at it. You should end up, you know, after you simplify that, you take the square root of it. You're also, this is all under the radical, right? This is all under the radical, right? This is all under the radical. So basically you would get this, you get 4t to the third plus 1. After you take the square root, that's going to go away. This has to be then written as t to the 3 halves power, and then when you split that up, you get 4t to the third over t to the 3 halves plus 1 over t to the 3 halves. Well, then that changes to be 4t. Let's see, that's going to be t to the 3 halves there, I think, right? And then plus t to the minus 3 halves, yeah. And so that is what Michael has over here, right? You guys see what's going on with that? So that's where he's getting all of that, right? 4t to the 3 halves plus t to the minus 3 halves. Right? So same thing, just a sort of a different way of getting there, but we do get the same thing. And then once you've gotten to that point, then the integral itself, right, doing that antiderivative is really not that bad. It's just a power rule situation. And then you got to plug in all the numbers, right, do all that stuff. And eventually you get to the, you know, simplified final answer there, which is pretty big, 1200, 1215. I would imagine this curve is probably pretty big. And then you kind of have to picture, like, what does the curve look like? And then also what happens when you revolve that whole thing around the x-axis. So it's going to end up giving a pretty big surface area. So that's the only example that we had of surface area, but it's a good one. I mean, it kind of shows you how to deal with this and reminds us about how to look, or to look for those perfect square trinomials in problems like this.